Our home in the cosmos is stranger than we ever imagined. It is not just the Milky Way floating in an empty void, but part of a colossal, gravitationally bound metropolis of galaxies known as the Virgo Supercluster. Picture, if you will, a web so vast it contains over 100 galaxy groups and clusters, with our own local group as just one quiet suburb in an immense cosmic city. By staying until the end, you will journey to the very edge of our understanding and confront 25 of the universe's deepest secrets. We will uncover why the motions of galaxies hint at an invisible, ghostly substance that makes up most of the mass around us. We will be pulled toward a mysterious point in space with a gravity so strong it defies explanation. How can a region of space larger than our minds can comprehend be almost completely empty? What creates bursts of radio energy so powerful they outshine entire galaxies in a millisecond? The answers are not simple, and in many cases they do not yet exist. That is the thrilling frontier we are about to explore. Are you ready to question everything you think you know about the universe? This cosmic city should be flying apart. The sheer speed at which galaxies orbit within the Virgo Supercluster creates a centrifugal force so powerful that the visible matter, all the stars and glowing gas we can see, is utterly insufficient to hold it together. There is simply not enough glue. Yet the supercluster remains bound, its structure intact against the relentless pull of the expanding universe. This glaring discrepancy points to a profound truth, the first of our great mysteries. Most of the mass in our supercluster, and indeed the entire universe, is completely invisible. We call this ghostly substance dark matter. Think of it like this. You are watching a merry-go-round at night, seeing only the glowing lights on the spinning platform. From the speed and pattern of those lights, you can calculate how much the entire structure must weigh to keep from tearing itself apart. Your calculation gives you a number, but when you add up the weight of just the lights you see, it is a tiny fraction of that total. The only logical conclusion is that the majority of the merry-go-round's mass is made of something you cannot see, something dark and heavy that provides the necessary gravitational anchor. This is precisely the puzzle astronomers face with the Virgo Supercluster. The glowing galaxies are just the lights, and the dark, heavy structure holding them together remains hidden from our telescopes. We know dark matter is there because of its gravitational signature. One of the most compelling pieces of evidence comes from a phenomenon called gravitational lensing. The immense gravity of a massive object, like a cluster of galaxies, warps the very fabric of space-time around it. This warping acts like a lens, bending and distorting the light from galaxies that lie far behind it. By studying the pattern of this distortion, scientists can map the total mass of the foreground cluster. Time and again, these maps reveal a massive, invisible halo of matter extending far beyond the cluster's visible stars. A halo whose gravitational pull is necessary to create the lensing effect we observe. So we can map its influence, we can calculate how much of it exists, and we know it makes up roughly 85% of all matter in the cosmos. But we have no idea what it actually is. It does not emit, absorb, or reflect any form of light or electromagnetic radiation. It seems to interact with ordinary matter only through gravity, passing through our planet, our homes, and our bodies as if we were not even there. Countless experiments deep underground and in space are searching for a hypothetical dark matter particle, but so far it has eluded every direct detection. This means the very foundation of our cosmic neighborhood, the Virgo Supercluster itself, is built upon a substance that is, for now, entirely mysterious. We are living in a house whose walls and framework we cannot see or touch, only feel through the force that holds everything in place. But the mystery of gravity in our supercluster does not end with dark matter. Our entire galaxy, along with thousands of others, is caught in a relentless river of motion. all flowing toward a single, unseen point in the distant cosmos. We are being pulled at over 2 million kilometers per hour toward something we cannot see. This is the second great mystery, the enigma known as the Great Attractor. For decades, astronomers mapped the motions of galaxies and found a consistent, puzzling drift. Every galaxy in our local neighborhood, including the Milky Way and Andromeda, shows a peculiar velocity, a shared motion on top of the general expansion of the universe. It is as if every leaf in a forest stream is drifting not just with the current, but also being tugged by a hidden waterfall downstream. The source of this colossal pull lies in the direction of the constellations Centaurus and Norma, behind the dense plain of our own Milky Way, an area so obscured by interstellar dust and stars that it is like trying to see a distant city through a thick fog. This zone of avoidance long hid the truth. What we eventually found there was the Norma cluster, a massive gathering of galaxies, but its visible mass is not nearly enough to account for the tremendous gravitational force we feel. The Great Attractor must be something far greater. The discovery was solidified by studying the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light serves as a universal reference frame. By measuring tiny temperature variations in this background radiation, scientists can detect how vast collections of matter are subtly shifting the light's frequency, a phenomenon known as the kinetic Sunyaev-Zeldovich effect. These measurements confirm the dark flow, the bulk motion of entire galaxy clusters toward the Great Attractor. So what is it? The leading theory suggests it is an immense concentration of dark matter, a gravitational focal point so dense it dominates the local geometry of the supercluster. It could be a supercluster within the supercluster, a knot in the cosmic web of such staggering scale that its gravity orchestrates the motion of everything around it. But there are more radical ideas. Some cosmologists have proposed that the pull might originate from a structure so massive and distant it lies beyond the horizon of our observable universe, an unimaginably large mass whose gravity somehow reaches across the void to influence us. This idea pushes the boundaries of physics itself. For now, the Great Attractor remains a shadow in the fog, a dominant force whose true nature is hidden by the very galaxy we call home. We feel its pull in our bones, or rather, in the very motion of our stars, yet its core is a secret the universe is still keeping. Yet this immense pull toward a hidden mass is not the only way gravity has sculpted our supercluster into bizarre forms. In another region, it seems to have done almost the exact opposite. Drifting through the constellation of Boötes, the herdsman, is a sphere of near-nothingness so vast it could swallow thousands of galaxies like our own. This is the Boötes void, a cosmic desert roughly 330 million light-years across. To grasp its scale, if you place the Milky Way at its center, the nearest edge of this emptiness would be over 160 million light-years away in every direction. In a universe where matter is arranged in a great cosmic web of filaments and clusters, this void is a staggering whole. Based on our understanding of how structure formed after the Big Bang, a region this size should contain around 2,000 galaxies. Instead, astronomers have found only a few dozen, scattered like lonely islands in an ocean of darkness. The question is not just why it is so empty, but what powerful force could have cleared it out. One possibility lies in the very earliest moments of the cosmos. The distribution of matter we see today is believed to have been seeded by tiny quantum fluctuations, microscopic ripples in the density of the primordial universe. These ripples were stretched to enormous scales by inflation, the universe's rapid expansion, creating the blueprint for galaxies and voids. Perhaps the Boötes void is simply an extreme statistical outlier, a random low-density patch that was amplified to a monstrous scale. It is like rolling a die an infinite number of times. Eventually, against all odds, you might get a sequence of 1,000 ones. The void could be our universe's improbable roll of the dice. But its sheer size makes some scientists wonder if a more dynamic process was at work. Could the combined gravity of the surrounding supercluster have actively drained this region over billions of years, pulling galaxies out like a cosmic tide? Or does its existence hint at something more exotic happening in the fabric of spacetime itself? There are even speculative, though highly controversial, ideas that such a void could be the result of a Type 3 civilization on the Kardashev scale, one that has harnessed the energy of entire galaxies. In this thought experiment, such a civilization might theoretically rearrange galaxies into a dense shell around their territory, leaving a vast, engineered emptiness at the center. While there is no evidence for this and natural explanations are far more likely, the void's existence forces us to question the limits of our models. It stands as a silent monument to the fact that the universe, even in its large-scale structure, is capable of producing anomalies of breathtaking scale. What other immense blanks might be waiting on the map of our supercluster, and what do they tell us about the rules or the exceptions that built our home? The profound emptiness of the Boötes void forces us to reconsider how matter arranges itself on the grandest scales, but the mysteries of gravity become even more intimate and puzzling when we look at the individual galaxies within our supercluster. Every spiral galaxy, including our Milky Way, harbors a secret in its very spin, a secret that whispers of the unseen. According to the laws of gravity as defined by Newton and refined by Einstein, stars orbiting a galaxy should behave like planets orbiting a star. Those close to the luminous center, where most of the visible mass is concentrated, should whip around at high speeds. Stars farther out in the sparse galactic suburbs, however, should orbit much more slowly, their velocity dropping off in a predictable curve as the gravitational grip of the central mass weakens with distance. This is not what we observe. When astronomers first measured the rotation curves of spiral galaxies by tracking the motion of stars and gas clouds, they found something astonishingly counterintuitive. The orbital speeds did not fall off. Instead, the rotation curve remained flat. Stars at the very edge of a galaxy's visible disk were orbiting just as fast as those near the center, as if held in place by an invisible hand. This was the first concrete, localized evidence that something was profoundly wrong with our understanding of mass. The visible galaxy, all its stars and glowing gas, simply does not contain enough gravity to keep those high-speed outer stars from flying off into intergalactic space. The only way to explain the flat rotation curve is to propose that each galaxy is embedded within a massive, spherical halo of invisible matter, a halo that extends far beyond the galaxy's luminous edge. This dark matter halo provides the extra gravitational pull needed to keep the outer stars whipping around at breakneck speeds. It is the cosmic equivalent of discovering that a spinning ice skater's arms are being held by invisible wires, allowing them to maintain their speed regardless of how far they extend. This galaxy rotation anomaly became the cornerstone of the dark matter hypothesis, offering a direct and repeatable observation that demanded an unseen source of gravity. Yet, not every scientist is convinced that an invisible particle is the only answer. A small but persistent group of researchers champions an alternative idea, known as modified Newtonian dynamics or MND. This theory proposes that our understanding of gravity itself is incomplete, especially in the extremely weak gravitational environments found at the edges of galaxies. Instead of invoking dark matter, MND suggests a slight tweak to Newton's laws, a modification that would naturally produce flat rotation curves without any extra mass. Proponents argue that MND can accurately predict the rotation speeds of many galaxies based solely on their visible stars and gas, a compelling argument for simplicity. The debate between dark matter and MND is one of the most fundamental in modern astrophysics. It is a clash of philosophies, one seeking to find new particles that make up the cosmos, the other seeking to rewrite the foundational rules of motion. While most evidence from galaxy collisions to the cosmic microwave background strongly favors the dark matter model, the persistence of MUND highlights a crucial truth: we are still deciphering gravity's full story. The silent spin of every galaxy in the Virgo Supercluster is a direct challenge, a puzzle written in the motion of stars that we have yet to fully solve. If the silent spin of galaxies is a whisper of the unseen, then some galaxies in our supercluster are outright ghosts. Drifting through the dense Coma cluster, a crowded neighborhood of over 1,000 galaxies, is an object called Dragonfly 44. Seen through a powerful telescope, it is a vast, faint smudge of light, a cosmic phantom so dim it was only discovered in 2015. This is an ultra-diffuse galaxy, a class of objects that defy every expectation. Dragonfly 44 is as wide as our Milky Way, spanning some 60,000 light-years, yet it contains less than 1% of the stars. Its light is so thinly spread that if you lived on a planet inside it, your night sky would be nearly empty, a profound and lonely darkness punctuated by only a few distant pinpricks. The immediate question is how such a thing can exist. How can a galaxy gather enough raw material to reach the size of the Milky Way, but then fail spectacularly at the one thing galaxies are supposed to do: make stars? One theory points to its violent environment. The Coma cluster is a gravitational maelstrom. Perhaps Dragonfly 44 was a normal galaxy long ago, but as it plunged through the cluster's hot, dense intergalactic gas, a process called ram pressure stripping violently tore away its star-forming fuel. What remains is a stellar skeleton, a galaxy that was gutted by its surroundings. Other theories suggest these ghosts are ancient relics, galaxies that formed in patches of the early universe that were unusually quiet and devoid of the gas collisions needed to spark prolific star birth. They simply never got going, but the deepest mystery of Dragonfly 44 was revealed not by its visible stars but by their motion. When astronomers measured the velocities of its few star clusters, they made a staggering calculation. To keep those clusters from flying apart, the galaxy must possess a mass comparable to the Milky Way. Since its starlight accounts for almost none of that mass, the conclusion was inescapable. Dragonfly 44 is almost entirely made of dark matter. Over 99.99% of its substance is the invisible, mysterious kind. This turns galaxy evolution on its head. We thought dark matter halos were the scaffolds upon which luminous galaxies were built, but here is a scaffold of immense proportions that, for reasons unknown, never attracted more than a ghostly wisp of visible matter. It is a dark matter galaxy in almost pure form, a hidden titan wearing only the faintest veil of stars. Its existence forces us to ask, are these ghosts common? And if so, does the Virgo Supercluster contain legions of these dark dominions, invisible kingdoms of matter that have been hiding in plain sight, masquerading as nothing more than faint flaws in the glass of our telescopes? But the cosmic web is not just a random tangle. When astronomers began mapping the grand architecture of the Virgo Supercluster, they noticed something deeply unsettling about the threads themselves. The vast filaments of galaxies, and even the individual clusters strung along them, appear to be aligned with one another over distances that beggar belief. It is as if you dropped 1,000,000 needles from a great height and found upon landing that most of them were pointing in roughly the same direction. This large-scale alignment defies our most basic assumption about the universe, the cosmological principle. This principle states that on the largest scales, the universe should be homogeneous and isotropic, meaning it should look roughly the same in every direction, with no preferred axis or special place. These alignments, stretching for hundreds of millions of light-years, suggest a kind of cosmic grain, like the weave in a piece of fabric, etched into the structure of reality itself. So what could possibly have imprinted such a pattern on the infant universe? One compelling idea points to the universe's very first moments. The seeds for all cosmic structure, from stars to superclusters, are believed to have been planted by quantum fluctuations, microscopic ripples in the fabric of spacetime that were inflated to astronomical sizes during the Big Bang. But what if those initial fluctuations were not perfectly random? What if they carried a subtle directional preference, a whisper of spin or polarization from the primordial quantum foam? This faint initial bias could have been stretched across the cosmos, dictating the preferred axis along which gravity would later pull matter into filaments and clusters. Another, even more exotic possibility involves primordial magnetic fields. These would be magnetic fields generated in the first fractions of a second after the Big Bang, threading the entire infant universe. While incredibly weak, such fields could have acted like invisible guide wires, influencing how ionized gas flowed and collapsed in the early cosmos, gently steering the formation of structure along preferred lines. The most radical interpretation, however, pushes the boundaries of cosmology itself. If the alignments are real and pervasive, some theorists wonder if they could be a fossil imprint from a universe that existed before our own Big Bang, a scar from a prior cycle of cosmic contraction and expansion that set the initial conditions with a built-in spin. While highly speculative, this idea forces us to confront the ultimate origin of everything we see. The silent, aligned filaments of our supercluster are more than just roads of galaxies. They may be the longest fossil records in existence, holding clues to the universe's first breath and perhaps even to what came before that first breath. The silent alignments of the cosmic web are a fossil imprint from the dawn of time, but some signals from our supercluster are not ancient echoes. They are sudden, violent screams. In a fraction of a blink, a source can release more energy than our sun will emit in 80 years. A brilliant flash of radio waves that vanishes before anyone can even turn to look. These are fast radio bursts, and their origins are one of the most urgent puzzles in modern astronomy. The first was discovered in 2007, buried in archival data from a radio telescope in Australia, and for years they were considered rare, one-off anomalies. But as our detection methods improved, we realized these events were happening all the time, perhaps thousands of times a day across the entire sky. The key breakthrough came when astronomers found a repeater, a source that fired off multiple bursts from the same patch of sky. This proved they were not just catastrophic explosions, but phenomena that could happen again and again. Crucially, some of these repeating bursts have been traced to locations within our own galactic neighborhood, the Virgo Supercluster, making them not just distant curiosities but local mysteries. So what could possibly generate such staggering power in mere milliseconds? The leading suspects are some of the universe's most extreme objects. A prime candidate is the magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from a credit card from halfway across the Milky Way. Theorists suggest that starquakes on the surface of a magnetar, or sudden rearrangements of its insane magnetic field, could unleash these focused blasts of radio energy. Other models involve collisions between neutron stars or the violent demise of a neutron star as it collapses into a black hole. Yet the sheer diversity of the burst, some repeating in erratic patterns, others appearing just once, suggests we might be dealing with multiple cosmic culprits. This has inevitably opened the door to more speculative ideas. Could the precise, repeating patterns of some bursts be artificial in nature? Some have wondered, cautiously, if they could be signatures of advanced technology, perhaps power beams for alien light sails propelling spacecraft across interstellar distances. While there is no evidence for this, and natural explanations are always preferred, the idea highlights just how extraordinary these signals are. Even more exotic are theories involving cosmic strings, hypothetical, incredibly dense defects in spacetime left over from the universe's birth. The vibration or snapping of such a string could, in theory, produce a titanic release of energy. The core challenge is their fleeting nature. By the time our telescopes register the burst and swing to look, the afterglow has faded, leaving only a ghostly fingerprint in our data. Each burst is a cosmic flare gun fired in the dark, and we are left scrambling to find where the light came from. Every new detection is a clue, a piece of a puzzle that is forcing us to rethink the most energetic physics in the cosmos, happening right in our own supercluster's backyard. These fleeting radio screams hint at a violent present, but our own galactic center holds evidence of a cataclysm that unfolded over a far grander timescale. Emanating from the very heart of the Milky Way are two colossal, ghostly orbs of high-energy radiation, each one towering 25,000 light-years above and below the galactic plane. These are the Fermi bubbles discovered in 2010 by the Fermi Gamma Ray Space Telescope, and they form a vast hourglass structure that dwarfs our entire visible galaxy. They are not made of stars or gas we can see in ordinary light, but are instead revealed by a faint, uniform glow of gamma rays, the most energetic form of light in the universe. Their very existence tells us that our seemingly quiet galactic neighborhood was once the site of a titanic explosion, an eruption of such force that it punched through the dense gas of the galactic disk and sent shockwaves echoing into intergalactic space. The question that has captivated astronomers ever since is a simple one: what was the engine of this apocalypse? The prime suspect sits right at the bubble's base, the supermassive black hole known as Sagittarius, a star. While it is relatively quiet today, it may have been a different beast millions of years ago. One leading theory suggests a past episode of violent feeding. If a large cloud of gas or even a star ventured too close, it could have been torn apart in a spectacular tidal disruption event, sending a torrent of matter swirling into the black hole's accretion disk. This feast would have triggered a colossal outburst of energy, not from the black hole itself, but from the superheated material just outside its event horizon. This energy could have been channeled into two powerful jets, perpendicular to the galactic disk, which then inflated these massive bubbles of gamma ray emitting gas over hundreds of thousands of years. It would be a fossil jet, a relic of our black hole's more active youth. But there is a compelling alternative story, one not of a single monster's outburst but of a frenzied crowd. The galactic center is a crowded stellar metropolis, and astronomers have found evidence of periods of intense star formation in the past. If millions of years ago, a wave of massive, short-lived stars were born all at once, their collective fate would have been spectacular. These giant stars would have lived fast, died young, and exploded as supernova in rapid succession. This starburst could have created a galactic wind so powerful it blew a giant cavity out of the galactic disk, creating the bubbles we see today. The gamma rays would then be produced by high-speed particles, accelerated by the countless shock waves from these stellar explosions, slamming into the slower gas of the interstellar medium. So which is it, the belch of a black hole or the combined breath of a generation of dying stars? The evidence is still being weighed. The bubble's sharp edges and symmetrical structure favor a sudden, directed event like a black hole jet. Yet the chemical fingerprints within the bubbles might better match the enriched material blown out by supernova. This mystery is more than an academic debate. It is an archaeological dig into our galaxy's biography. The Fermi bubbles are a scar, a testament to a time when the Milky Way was a far more volatile place. They force us to see our home not as a static island, but as a dynamic entity with a violent history, capable of eruptions that reshape its very structure and send ripples through the local web of the Virgo Supercluster. Yet our place within this violent cosmic web is more peculiar than we realized. We are not floating in an average part of the universe, but are instead residents of a sprawling cosmic suburb, a quiet neighborhood of nothing. This is the KBC void, named for the astronomers Keenan, Barger, and Cowie who identified it. While the Boötes void is a distant desert, the KBC void is our own local underdensity, a spherical region roughly 2 billion light-years across where the concentration of galaxies is significantly lower than the cosmic average. Think of the universe's matter distribution as a sponge. Most galaxies live in the dense, wet strands of the sponge. The KBC void is the large, dry bubble we happen to be sitting inside. For years, cosmologists operated on the assumption that the Milky Way's location was typical, a necessary starting point for measuring the universe. The discovery of this immense local hole turns that assumption on its head. It means our view of the cosmos is fundamentally skewed. We are peering out at the universe from inside a bubble, and that has profound consequences for one of the most critical numbers in all of science, the Hubble constant. This constant measures how fast the universe is expanding at the present time. For decades, two primary methods have been used to pin down its value. One method looks at the cosmic microwave background, the ancient afterglow of the Big Bang, and extrapolates forward to predict today's expansion rate. The other method uses relatively nearby objects like pulsating stars called Cepheids and exploding stars called Type 1, a supernova, to measure the expansion directly. These two methods, one looking at the infant universe and one looking at the modern universe, should agree. They do not. They disagree by a significant and stubborn margin. This discrepancy is known as the Hubble tension, and it represents a genuine crisis in cosmology, suggesting a flaw in our standard model of the universe. Here is where our address in the KBC void becomes crucial. If we are living in a local underdensity, a giant hole, then gravity's pull on our region is weaker than average. Galaxies just outside our void are being pulled toward the denser walls around us, making them appear to be moving away from us slightly faster than they truly are relative to the universe's overall expansion. It is like measuring the speed of cars from a valley. The cars on the ridges above seem to be moving faster because they are on higher ground. This local effect could be biasing our nearby measurements of the Hubble constant, making the universe seem to be expanding faster from our perspective than it actually is on a global scale. The void, in essence, could be creating a cosmic optical illusion. If this is true, it might resolve the tension, suggesting the two methods are measuring slightly different things, one a local, biased rate and one the true global rate. But the KBC void's existence is itself controversial. Is a void 2 billion light-years across even possible under our current understanding of cosmic structure formation? Some sophisticated computer simulations of the universe suggest such a large underdensity is extremely unlikely, a 1 in 1,000 chance. Its confirmed existence would force us to revise those models, implying the cosmos is even lumpier on large scales than we thought. So we are left with a fascinating puzzle. Either we live in a statistically improbable cosmic bubble that is skewing our most fundamental measurements, or our standard model of cosmology is missing a crucial piece of physics that would allow such voids to form naturally. Our very address in the Virgo Supercluster has placed us at the center of a debate that could redefine the expansion history of everything. Our peculiar position within a cosmic void forces us to question the very expansion of space, but there is a force at work far more dominant than any local emptiness. The universe is not just expanding, it is accelerating, and this acceleration is actively reshaping the future of our entire supercluster. This mysterious driver is dark energy, a repulsive force that permeates the very vacuum of space. While its influence is universal, its effects are written in the motion of galaxies right here in our cosmic neighborhood. When astronomers measured the recession speeds of distant galaxy clusters within and beyond the Virgo supercluster, they expected to see the expansion slowing down over time, pulled by the collective gravity of all the matter in the cosmos. Instead, they found the opposite. The most distant clusters are speeding away from us faster than our models predicted, as if some invisible foot is pressing down on the cosmic accelerator. This discovery, which earned a Nobel Prize, means dark energy is winning a cosmic tug of war against gravity's pull. So what is it? the leading and simplest explanation is Albert Einstein's cosmological constant, a fixed property of empty space itself. In this view, every cubic centimeter of the vacuum, even the empty space between stars in your living room, contains a tiny, intrinsic energy that pushes outward. While this energy is negligible on small scales across the vast gulf between superclusters, it adds up to an overwhelming force, but is it truly constant? Some theories suggest dark energy could be a dynamic field, nicknamed quintessence, that changes in strength over time. It could be weakening or even growing stronger. Others propose it is not a new energy at all, but a sign that our understanding of gravity, Einstein's theory of general relativity, breaks down on the largest scales. Perhaps gravity itself behaves differently across cosmic distances, mimicking the effect of an accelerating expansion. The implications for the Virgo supercluster are profound and ultimately lonely. As the acceleration continues, the space between galaxy clusters will stretch at an ever-increasing rate. In the far future, the distant galaxies we see today will have their light stretched so far it shifts beyond the visible spectrum, then beyond radio, becoming undetectable. Eventually, the space between galaxy clusters will expand faster than light can cross it, isolating each cluster in its own observable universe. Our supercluster, bound by gravity, will remain together, but it will become an island in an ever-darkening sea. All other superclusters will vanish over the cosmic horizon, their light never to reach us again. The Virgo supercluster will be all there is to see, a solitary island of stars in an infinite, expanding blackness. Dark energy is not just a curious fact, it is the force writing the final chapter of our cosmic story. A story that ends with every island of light drifting apart into eternal, silent isolation. The silent isolation awaiting our supercluster is shaped by forces we cannot see, but another invisible power is woven through the very fabric of every galaxy. Stretching for tens of thousands of light years, organized and coherent, are immense magnetic fields. They are the silent architects of cosmic structure, influencing how gas collapses to form stars and guiding the paths of high-energy particles. Yet their origin is a profound puzzle. How does a galaxy, a swirling disk of tenuous gas and stars, generate and maintain such a vast, organized magnetic structure? The leading explanation is the galactic dynamo theory. It is a beautiful and complex idea. Picture the galaxy as a giant, slow-motion engine. The differential rotation of the galactic disk, where inner regions spin faster than outer ones, acts like a set of spinning gears. This motion, combined with turbulent convection from supernova explosions and star formation, can stretch and twist weak, primordial magnetic seed fields. Over hundreds of millions of years, this process can amplify those feeble seeds into the large-scale, coherent fields we detect today. It is a self-sustaining cycle where the motion of conductive plasma generates electrical currents, which in turn reinforce the magnetic field. But the theory faces significant challenges. The process is incredibly delicate, requiring just the right conditions of turbulence and rotation to avoid tangling the field into a chaotic mess. Computer simulations struggle to reproduce the beautifully ordered spiral magnetic patterns we observe tracing the arms of galaxies like our own. Furthermore, we have detected magnetic fields in the most tenuous places imaginable, the faint intergalactic medium within the filaments of the Virgo supercluster. This is the near-perfect vacuum between galaxy clusters, a space so empty it makes the void of space within a solar system seem crowded. Finding organized magnetism here is like detecting a persistent, faint hum in a silent, abandoned cathedral. These fields cannot be generated by a galactic dynamo, as there is no rotating disk or concentrated star formation to power it. So where did they come from? One possibility is that they are relics, stretched and diluted remnants of fields that were blown out of galaxies by powerful winds from supernova or active black holes, seeding the cosmos with magnetism during an earlier, more violent epoch. Another, more radical idea is that they are truly primordial, generated during the universe's first moments in processes like phase transitions in the hot, dense plasma of the Big Bang itself. If true, these faint intergalactic fields would be fossils from the universe's infancy, a subtle magnetic memory imprinted on the cosmos before the first stars ever flickered to life. Their role is potentially immense. These large-scale magnetic fields could influence the formation of galaxies by providing support against gravitational collapse, slowing down star birth. They could channel cosmic rays, the high-energy particles speeding across the universe, acting as invisible highways for the most energetic processes we know. We are only beginning to map this hidden magnetic skeleton of our supercluster. Each new measurement reveals a cosmos threaded with invisible lines of force, a silent, dynamic presence that has been shaping cosmic evolution from the very beginning, a fundamental ingredient in the recipe of reality we are only just learning to read. The invisible magnetic fields that thread our supercluster are a subtle force, but sometimes gravity itself seems to behave in ways we cannot explain. Decades ago, as our first robotic ambassadors drifted beyond the planets, they sent back a tiny, persistent puzzle. The Pioneer 10 and 11 spacecraft, after swinging past Jupiter and Saturn, were on trajectories out of the solar system. Scientists tracking their precise positions noticed something was off. Both probes were experiencing a minute but constant deceleration toward the Sun, a tiny tug backward of about 1/10 billionth of the force of gravity we feel on Earth. This was the Pioneer anomaly, a whisper of a discrepancy that refused to go away. For years, it fueled speculation about new physics, perhaps a flaw in our theory of gravity itself that only became apparent in the vast, quiet expanse of interstellar space. Could Einstein's general relativity need a tweak at these scales? The mystery captivated physicists, as a solution might rewrite the rules for the entire cosmos. Eventually, after painstaking analysis, a more mundane culprit was identified. The subtle, uneven radiation of heat from the spacecraft's radioactive power generators was creating a tiny photon thrust, pushing the probes backward just enough to account for the anomaly. It was a thermal recoil, not a new law of physics. Yet the story did not end with a simple answer. The long investigation revealed just how difficult it is to account for every single force acting on a spacecraft over decades and billions of kilometers. It highlighted a profound truth: our confidence in the laws of physics is built upon our ability to model every last detail, and in the emptiness of space, we are still learning what those details are. This lesson echoes far beyond our solar system. While the Pioneer case was solved, the question remains: could there be other, similar anomalies hiding in the motions of objects on a far grander stage? When we look at the trajectories of entire galaxies within the Virgo Supercluster, are we absolutely certain we have accounted for every form of gravitational pull, every nudge and tug? The apparent pull of the Great Attractor and the strange flows of dark matter suggest we have not. The Pioneer anomaly serves as a cautionary tale and an inspiration. It reminds us that unexplained accelerations, however small, are clues. They are the universe pointing to a gap in our understanding. If a tiny thermal effect could mimic a gravitational mystery for decades, what other subtle forces or unknown masses might be subtly bending the paths of stars and galaxies within our supercluster, effects we simply lack the precision or perspective to see? The search for such discrepancies is now a central part of cosmology, a hunt for any motion that cannot be explained by the map of visible matter and the predicted halos of dark matter. Each anomaly could be a signpost pointing toward something entirely new, a gravitational ripple from a hidden dimension, the effect of a previously unknown particle, or evidence that gravity itself works differently across the millions of light years that separate galaxy clusters. The solved mystery of Pioneer tells us to look closer, because sometimes the key to the largest puzzles lies in mastering the smallest details. The universe has a speed limit for particles, and we have found messengers that seem to break it. This is the mystery of the GZK cutoff, named for the physicists Greisen, Zatsepin, and Kuzmin. It is a fundamental barrier imposed not by technology but by the very fabric of space. The theory states that a proton traveling through the cosmos at near light speed, if it possesses an energy above a certain staggering threshold, should not be able to travel very far. Why? Because it would be constantly bumping into the faint, cold glow of the cosmic microwave background radiation, the afterglow of the Big Bang that fills every cubic centimeter of the universe. Each collision would chip away at the proton's monumental energy, slowing it down over a relatively short cosmic distance of about 150 million light-years. According to this, any ultra-high energy cosmic ray we detect here on Earth should originate from within our own local supercluster, the Virgo Supercluster, or from just beyond its borders. The universe itself should be opaque to these extreme particles, yet our detectors have recorded them. These are not just high-energy particles, they are the most energetic things we have ever observed, subatomic bullets carrying the kinetic energy of a professionally thrown baseball, all compressed into a single proton. They hit our atmosphere with a force that triggers a cascade of secondary particles, a shower that our observatories can trace. The baffling part is that when astronomers trace back the paths of some of these ultra-high energy events, they point to seemingly empty space, with no obvious powerhouse like a galaxy or a quasar in the immediate vicinity. This presents a double mystery. First, what cosmic engine could possibly accelerate a single proton to such an insane velocity? The forces involved are almost unimaginable, far beyond anything our most powerful particle colliders can produce. The usual suspects are the most violent objects we know: active galactic nuclei, where supermassive black holes spew jets of plasma at nearly light speed, could act as natural particle accelerators on a galactic scale. Cataclysmic explosions like gamma-ray bursts or the mergers of neutron stars are also contenders, capable of unleashing unfathomable energy in a blink. But to reach the energies we see, these events would need to be perfectly tuned and monstrously powerful, even by their own extreme standards. The second, deeper mystery is how these particles made the journey to us at all. If they came from a source hundreds of millions of light-years away, outside our local supercluster, the GZK cutoff says they should have been slowed to a crawl by the cosmic microwave background long before they reached Earth. Their very detection suggests they either came from surprisingly nearby within our supercluster, which makes identifying their source even more urgent, or they are something other than protons, perhaps heavier atomic nuclei that interact with the background radiation differently. There is a more radical possibility, too. Perhaps our understanding of particle physics or the nature of spacetime itself needs revision at these extreme energies. Could Lorentz invariance, a cornerstone of Einstein's relativity that dictates how particles behave at near light speed, be slightly broken? Each detection is a message in a bottle, sent from the most ferocious engines in the cosmos. The bottle itself seems impossible, a vessel that should have dissolved in the sea of background radiation. Yet here it is, washing up on our shore, carrying a signature from a storm we cannot yet see. The most energetic particles in the cosmos defy a universal speed limit, but sometimes the universe's smallest building blocks hold secrets just as profound. Deep within the ancient stars of our Milky Way, and likely in galaxies across the Virgo Supercluster, lies a quiet but fundamental contradiction. The oldest stars act as cosmic time capsules, preserving the chemical composition of the early universe in their atmospheres. According to our meticulous models of Big Bang nucleosynthesis, the frantic cooking of light elements in the universe's first few minutes, there should be a specific amount of the element lithium. The math is precise, accounting for the density of protons and neutrons and the rapid cooling of the newborn cosmos. The predictions say these primordial stars should show a lithium abundance nearly 3 times higher than what we actually measure. This is the cosmological lithium problem, a stubborn deficit that has persisted for decades. It is not a small observational error. It is a glaring mismatch between our theory of the universe's birth and the forensic evidence preserved in starlight. So where did all the lithium go? One line of investigation looks inward to the stars themselves. Could stellar physics be destroying the lithium after the star forms? As a star ages, the convective currents in its outer layers can drag surface material down into the hotter interior, where temperatures are high enough to burn lithium in nuclear reactions. This process could, over billions of years, deplete the surface abundance we measure. But many of the stars we study are old, slow-burning dwarfs that should have very stable outer layers, making this kind of deep mixing difficult to explain. Perhaps the answer lies not in the stars, but in our understanding of those first 3 minutes. The calculations for Big Bang nucleosynthesis rely on our knowledge of nuclear reaction rates, some of which are incredibly difficult to measure in laboratories on Earth. Could there be an unknown or poorly measured nuclear reaction pathway that consumed lithium faster in the early universe than our models account for? Some physicists have proposed resonances in the interactions between beryllium and helium nuclei that could have siphoned off lithium, but so far, laboratory results have not confirmed this. Then there is the more exotic possibility, one that connects this missing matter to the universe's greatest mystery. What if the lithium was destroyed by dark matter? In some theoretical models, certain types of hypothetical dark matter particles could accumulate in the cores of ancient stars. Over time, these particles would annihilate each other, releasing energy that subtly alters the star's internal structure and temperature. This extra heat could enhance the mixing processes, dredging lithium down to be burned more efficiently than standard stellar models predict. In this scenario, the lithium deficit in a star's atmosphere becomes a potential fingerprint of dark matter interactions, a faint signal of the invisible universe etched in the chemistry of the visible one. The lithium problem is a beautiful example of a cosmological puzzle that bridges scales, from the universe-wide event of the Big Bang to the intimate physics within a single ancient star. It reminds us that the universe left a receipt for its creation, written in hydrogen, helium, and lithium. The fact that the numbers do not quite match means we are still learning to read the fine print, and that the oldest stars in our supercluster are still keeping secrets about their own origin story. The missing lithium in ancient stars points to a flawed recipe for the early cosmos, but another ingredient from that same era defies explanation entirely. At the heart of nearly every large galaxy in the Virgo Supercluster, including our own Milky Way, sits a supermassive black hole. These are not the remnants of dead stars, they are cosmic monsters with masses ranging from millions to billions of times that of our Sun. Their existence alone is staggering, but the real mystery is their birth certificate. We have found quasars, the blazing signatures of actively feeding supermassive black holes, shining from the universe's infancy when it was less than 1 billion years old. This presents an immense puzzle. How did something so monstrous grow so fast, so early? There simply does not seem to have been enough time in the young universe for a normal star to die, leave behind a black hole seed, and then slowly eat its way up to billions of solar masses. The clock just does not tick that quickly, so astronomers are forced to consider more dramatic origin stories. One compelling idea is known as direct collapse. In this scenario, the first generation of structures were not stars, but immense, pristine clouds of hydrogen and helium gas. Without heavier elements to cool and fragment efficiently, these clouds could have collapsed directly under their own gravity, skipping the star formation stage altogether and plummeting into a single, massive black hole seed weighing perhaps 10,000 suns or more. This heavyweight seed would then have a tremendous head start, allowing it to gorge on surrounding gas and grow to supermassive proportions within the available time. It is like planting a sapling versus a fully grown tree. The latter reaches maturity much faster. another theory sticks with stellar seeds but supercharges the process. Perhaps the first stars were not just big but unimaginably colossal, hundreds of times more massive than any star we see today. These behemoths would have lived brief, violent lives and collapsed into black holes of a few hundred solar masses. If these seeds then found themselves in a densely packed, gas-rich environment at the center of a young galaxy, they could have merged rapidly and fed voraciously in a perfect storm of growth. Think of it as a feeding frenzy in a cosmic pond stocked to the brim. The most exotic proposal, however, reaches back to the very first moments of time. Could these supermassive black holes be primordial? This theory suggests they were not born from stars or gas clouds at all, but were instead forged in the extreme densities and pressures of the Big Bang itself. Tiny fluctuations in that primordial soup could have collapsed directly into black holes of all sizes, with the largest ones settling into the hearts of proto-galaxies as ready-made anchors. This would solve the timing problem neatly, as they would have existed almost from the very beginning. Each theory has its challenges. The direct collapse model requires very specific, pristine conditions that may have been rare. The rapid growth from stellar seeds demands a nearly perfect, uninterrupted buffet of gas that is hard to sustain. And primordial black holes remain entirely hypothetical, with no direct evidence for their existence. Yet, these silent giants are there, their immense gravity dictating the orbits of stars and shaping the evolution of their host galaxies. Their premature appearance in the cosmic record is a glaring clue that our story of cosmic structure is missing a crucial, dramatic chapter, one written in the deep darkness of the first dawn. These silent giants sculpt their galaxies from within, but the story of a galaxy's life is also written in the vast, invisible atmosphere that surrounds it. Every spiral galaxy like our own is cocooned within an immense sphere of superheated gas, a diffuse halo that extends for hundreds of thousands of light years. This plasma is the galactic corona, a relic of the galaxy's formation and a reservoir for its future. For decades, models predicted these halos should be searingly hot, reaching temperatures of millions of degrees, heated by the relentless fury of stellar feedback. When massive stars explode as supernova, they blast winds of hot gas and radiation out into the void. Similarly, the supermassive black hole at the galaxy's core can erupt, pumping colossal energy into its surroundings. This feedback was thought to keep the halo gas at a rolling boil. Yet, when astronomers finally measured the actual temperatures of these halos using sensitive X-ray telescopes, they got a surprise. The gas was warm, yes, but not nearly as hot as it should be. It was lukewarm, a cosmic bathwater instead of a raging inferno. This is the missing heat problem, and it reveals a gap in our understanding of how energy moves through a galaxy. The models overpredicted the temperature by a significant margin. So where did all the energy go? One possibility is that our understanding of feedback is too simplistic. Perhaps supernova explosions and black hole jets are not as efficient at heating the halo as we assumed. Maybe the energy is being dissipated in ways we haven't accounted for, perhaps by generating large-scale magnetic fields or by driving turbulent motions that radiate the heat away more quickly. Another, more intriguing idea involves the cosmic web itself. The halos are not isolated, they are connected by faint filaments of gas that weave throughout the Virgo Supercluster. Could this cooler gas from the intergalactic medium be constantly streaming into the halo, mixing with and cooling down the hotter material? It would be like a hot spring fed by a cold underground river, resulting in a tepid pool. This has profound implications for the life cycle of ordinary matter, what cosmologists call baryonic matter. Galaxies are not closed systems, they breathe. They expel gas through stellar winds, and they accrete fresh gas from the cosmic web to fuel new generations of stars. The temperature of the halo is the thermostat for this cycle. If the halo is too hot, incoming gas cannot cool and condense to form stars, starving the galaxy. If it is too cool, gas can cool too rapidly, potentially leading to runaway star formation. The observed lukewarm state suggests a delicate, self-regulating balance is at work, one that our current simulations of galaxy evolution struggle to replicate. This missing heat is more than a calibration error. It is a clue that the conversation between a galaxy and its environment, between stellar death and stellar birth, is far more nuanced and subtle than we ever imagined. The galaxy's missing heat reveals a delicate balance, but another faint glow from the dust between the stars presents a different kind of puzzle. Across the Milky Way and in other galaxies, a subtle, anomalous microwave emission hums at frequencies our eyes cannot see. It is not the sharp radio scream of a fast burst or the searing X-ray glow of hot gas. This is a diffuse, enigmatic whisper in the microwave band of the spectrum, and it does not match the signature of any known astrophysical process. For decades, astronomers catalogued the various components of the interstellar medium, the stuff between stars. They mapped the synchrotron radiation from electrons spiraling around magnetic fields and the thermal radiation from warm dust grains heated by starlight. Yet, when they subtracted all these known sources from the total microwave signal, a persistent residue remained. This is the anomalous microwave emission, a ghost in the machine of our cosmic maps. Its very existence means there is a physical process at work in the vast interstellar clouds that we have not yet identified, a process that converts energy into this specific band of microwave light. The hunt for the culprit has led scientists into the realm of the incredibly small. The leading suspects are not stars or gas clouds, but tiny, spinning molecules and specks of dust. One compelling theory points to a class of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH. These are flat, chicken wire-like molecules made of carbon and hydrogen, essentially tiny flakes of soot. They are thought to be abundant throughout the galaxy. When a pH molecule is struck by a single ultraviolet photon from a nearby star, it does not just heat up, it can begin to spin rapidly. This frantic rotation, happening billions of times per second, could then emit radiation at microwave frequencies. It is like a microscopic cosmic propeller humming in the void. An even more exotic candidate is nanodiamond. Yes, diamonds in space. These are carbon crystals only a few nanometers across, thought to form in the atmospheres of cool, carbon-rich stars and then be blown out into the interstellar medium. Some of these nanodiamonds have hydrogen atoms attached to their surfaces. When these hydrogen atoms are hit by starlight, they can set the entire tiny diamond spinning, and that spin could also produce the anomalous microwave signal. It is a strange and beautiful thought that the faint microwave glow of our galaxy might be, in part, the collective hum of countless spinning nanodiamonds scattered between the stars. The detective work is incredibly challenging because we cannot simply go out and grab a sample. Instead, astronomers must become forensic spectroscopists, studying the precise shape and intensity of the anomalous emission across many different microwave frequencies. They compare these fingerprints to laboratory measurements and theoretical models of how PAHs or nanodiamonds should behave. So far, the match is promising but not perfect. The signal seems to correlate well with regions rich in the specific infrared light that PAHs are known to emit, a strong clue. But confirming the source requires ever more precise observations from space-based observatories and advanced radio telescopes. This faint glow is more than a curiosity. It is a direct probe of the conditions within dark molecular clouds, the very nurseries where new stars and planets are born. Understanding what causes it tells us about the composition and physics of the raw materials that build solar systems. If it is from spinning PAHs, it confirms that the complex organic building blocks of life are not just present on planets, but are woven throughout the galaxy itself. If it is from nanodiamonds, it reveals a previously hidden phase of cosmic carbon, a glittering dust that forms in the hearts of dying stars. This anomalous microwave emission is a quiet message from the smallest things, a signal that reminds us the universe is full of subtle, unseen processes waiting for their story to be told. This faint glow from cosmic dust is a whisper from the small, but the structure of our own galactic neighborhood presents a challenge on a far grander scale. The Milky Way is not alone. It is orbited by dozens of smaller satellite galaxies, like the Large and Small Magellanic Clouds. For decades, the standard model of cosmology, known as Lambda CDM, made a clear prediction about these satellites. They should be arranged in a roughly spherical swarm, like bees buzzing around a hive, each following its own independent orbit dictated by the immense spherical dark matter halo that envelops our galaxy. This is not what we see. Instead, a majority of these satellite galaxies are aligned along a startlingly thin, vast plane, a great disk that slices through the Milky Way. Even more astonishing, our great neighbor, the Andromeda Galaxy, shows the same peculiar architecture, with many of its own satellites also orbiting in a thin, coherent plane. This is the satellite galaxy plane problem, and it strikes at the heart of our understanding of how structure forms in a universe dominated by dark matter. The Lambda CDM model is spectacularly successful at explaining the universe on the largest scales, from the cosmic microwave background to the distribution of galaxy clusters. But on the scale of individual galaxies and their satellites, it predicts a messy, chaotic distribution, the result of small dark matter clumps falling into the larger halo from all directions over billions of years. The existence of these thin, rotating planes of satellites is like throwing a handful of marbles into a bowl and finding they have all neatly arranged themselves into a single spinning ring. It should not happen by chance, so what force could be orchestrating this cosmic ballet? One possibility takes us back to the earliest pages of the universe's story. Could these planes be fossils from the process of galaxy formation itself? When galaxies form, they often pull in gas and smaller proto-galaxies along the vast filaments of the cosmic web. If our Milky Way and Andromeda each formed along a particularly dense filament, their satellites might have been drawn in along that same highway, preserving a flattened distribution to this day. It is a compelling idea, but simulations show that such planes are fragile, easily disrupted over time by gravitational interactions within the halo. They should not persist for the age of the universe. Another, more dynamic explanation involves the brutal history of galactic encounters. Perhaps these satellite planes are not primordial at all, but the debris from a colossal collision. If a large galaxy passed too close to the Milky Way billions of years ago, the immense tidal forces could have ripped it apart, stretching its stars and dwarf galaxies into a long stream that eventually settled into the disk-like structure we see today. This would make our satellite galaxies not independent entities, but siblings from a single, shattered parent. While evidence for such a major merger exists in our galaxy's distant past, it is difficult to explain why both the Milky Way and Andromeda would have experienced such similar plane-forming collisions. The most provocative implication, however, concerns dark matter itself. The Lambda CDM model relies on dark matter being cold and collisionless, meaning dark matter particles mostly pass right through each other and ordinary matter. This property is what allows dark matter halos to form those puffy, spherical shapes. If the satellite planes are real and long-lived, it might suggest that dark matter has properties we have not accounted for, perhaps interacting with itself through some unknown force that allows it to settle into disks. Or it could be a clue that we need to revise our models of how dark matter subhalos behave and merge. The silent, coordinated dance of these tiny galaxies around their hosts is a direct observational challenge to a foundational theory of modern cosmology. It is a reminder that sometimes the most telling clues are found not in the brilliant centers of galaxies, but in the quiet, orderly motion of their faintest companions. The silent, coordinated dance of satellite galaxies presents one challenge to our cosmic models. But the darkness around us holds another, even more fundamental contradiction. It is known as the too big to fail problem, and it strikes at the very predictions of our most powerful supercomputer simulations of the universe. According to the Lambda CDM model, our Milky Way's vast dark matter halo should be swarming with hundreds of smaller subhalos, clumps of dark matter that are the building blocks of galaxy formation. Among these, the simulations predict a specific number of especially massive subhalos, giants in the dark. They are dubbed too big to fail because their gravitational pull is so strong that, by all our understanding, they should easily have attracted enough gas to form bright, bustling dwarf galaxies visible from Earth. Yet when we look, we find far fewer of these luminous satellites than the simulations say we should. The dark matter giants are there in the calculations, but their brilliant counterparts are missing from our telescopes. This is not just a minor accounting error. It is a direct mismatch between the predicted dark architecture and the visible city lights. The problem lies in the density of these predicted subhalos. They are so massive and gravitationally powerful that even the intense radiation and stellar winds from early star formation, processes we call supernova feedback, should not have been strong enough to completely blow away all their gas and prevent the birth of stars. They were simply too big to fail at becoming galaxies. So why are they so dark? One line of investigation suggests our simulations of astrophysics might be incomplete. Perhaps supernova feedback is far more violent and efficient than we ever modeled. In this scenario, the first generation of stars inside these massive subhalos were incredibly energetic. When they exploded, their collective fury could have created galactic winds of unprecedented strength, scouring the subhalo clean of its star-forming gas in one colossal outburst. It would be like a hurricane so powerful it strips a fertile island down to bare rock, leaving it permanently barren. This would leave us with a massive, dense dark matter halo, but one that is utterly dark, a failed galaxy that never truly ignited. The other possibility is more profound. It questions the nature of dark matter itself. Our standard simulations use a model called cold, collisionless dark matter. This means the particles move slowly by cosmic standards, and crucially, they pass through each other and ordinary matter without interaction aside from gravity. This property allows dark matter to form very dense, cuspy centers in these subhalos. But what if dark matter is not perfectly cold and collisionless? Some alternative theories propose it might be slightly warm, meaning the particles move faster, which would prevent them from clumping as densely on small scales. Others suggest dark matter could have a tiny ability to interact with itself, a faint self-repulsion that would puff up the cores of subhalos, making them less gravitationally domineering. In these models, the subhalos would still exist, but they would be less dense, their gravitational grip weaker. This weaker grip would make it much easier for supernova feedback to blow out the gas, effectively dooming star formation from the start. The too big to fail problem would vanish, not because the astrophysics is more violent, but because the dark matter scaffolding itself is softer and less imposing. This cosmological conundrum forces us to look at the darkness in two ways. Is it an astrophysical story about the incredible power of stellar explosions to shape their own destiny? Or is it a fundamental physics story hinting that dark matter is more complex than a simple, inert ghost? The answer likely lies in a delicate balance between the two. Each faint, real dwarf galaxy we discover, and each massive, dark subhalo we infer, is a data point in this grand experiment. They are the cosmic equivalents of footprints, and right now, the size and depth of the prints do not match the weight of the creature we thought made them. This growing discrepancy in our cosmic accounting is not just a minor error, it is a crack in the foundation of modern cosmology. Two of the most trusted methods for measuring the universe's expansion rate, the Hubble constant, now give stubbornly different answers, and the rift is only widening with more precise data. One method looks back to the universe's infancy, analyzing the subtle patterns in the cosmic microwave background. By feeding this snapshot of the baby universe into our standard model of cosmology, we can extrapolate forward to predict how fast it should be expanding today. The other method uses cosmic landmarks within our local universe, like pulsating Cepheid stars and exploding Type 1, a supernova, to directly measure the expansion rate around us now. These are the gold standards of cosmic distance measurement. The problem is stark. The early universe method suggests a slower, more sedate expansion rate, while the local measurements consistently return a faster, more urgent one. The numbers disagree by enough that the chance this is a simple fluke is vanishingly small. This is the Hubble tension, and it represents a genuine crisis. If our most fundamental model of the cosmos cannot reconcile these two truths, it means something in our understanding is broken. Cosmologists are now forced to consider three unsettling possibilities. First, there could be unknown systematic errors hiding in our meticulous measurements. Perhaps there is something we do not yet understand about the Cepheid stars or the supernova that is subtly skewing our local ruler. Teams are checking and rechecking the data, but so far the discrepancy holds firm. The second and more thrilling possibility is that this tension is a sign of new physics. Our standard model, lambda CDM, might be incomplete. Perhaps dark energy is not constant but evolving, growing stronger over time. Maybe neutrinos have unexpected properties, or gravity itself behaves differently on cosmic scales than we think. This crack could be the entry point for a revolutionary discovery, but the third possibility brings us back to our own unusual address within the Virgo Supercluster. Could the local measurement be wrong, not because of faulty tools, but because our viewpoint is fundamentally biased? Remember the KBC void, that immense spherical region of underdensity we call home. If we truly reside in a billion light-year wide cosmic bubble where matter is thinner than average, then the gravitational landscape around us is unusual. The pull of surrounding, denser regions could be subtly accelerating the apparent recession of galaxies just outside our void. From our vantage point in the valley, the ridges seem to be racing away faster than they truly are relative to the universe's overall expansion. This local illusion could be inflating our measurement of the Hubble constant, creating the tension with the pristine, global view from the cosmic microwave background. The implications are profound. Either we have stumbled upon evidence that demands a rewriting of the cosmic rulebook, or we have discovered that our place in the supercluster is so statistically odd that it distorts our view of the entire cosmos. Both answers are extraordinary. One suggests a universe far more dynamic and mysterious than our models allow. The other suggests we are cosmic outliers, living in a rare, quiet neighborhood that tricks us into seeing a universe in a hurry. The Hubble tension is not an abstract puzzle for theorists. It is a direct challenge from the universe itself, a question written in the fleeing light of galaxies, asking us to decide if the problem is out there in the laws of physics or right here in the peculiar emptiness of our own home. The Hubble tension forces us to question our most basic measurements of the cosmos, but sometimes the missing piece of the puzzle might be hiding in our own backyard. For years, astronomers have tracked a peculiar clustering in the orbits of small, icy bodies in the distant solar system beyond Neptune. Their paths are skewed, shepherded as if by the gentle, persistent tug of an unseen giant. This is the hypothesized Planet 9, a world perhaps 10 times the mass of Earth, lurking in the frozen darkness hundreds of times farther from the Sun than we are. Its existence is inferred solely through gravity's subtle signature on other objects, a ghostly hand guiding the dance of ice from the shadows. The ongoing search for it is a masterclass in cosmic detective work, illustrating just how difficult it is to find a dark, massive object even within our own solar family. It must be sought not by its light but by the trails it leaves in the paths of others. This elusiveness is a powerful analogy for a far grander mystery. If we can struggle to find a planet-sized object in our own solar system, what dark, massive things might be drifting unseen through the vast halos of the Virgo Supercluster? Planet 9's proposed nature ranges from a rogue planet ejected long ago to something more exotic, a primordial black hole no larger than a grapefruit but containing several Earth masses. This latter idea opens a dizzying possibility. What if the dark matter halos enveloping galaxies are not just clouds of unknown particles, but also sprinkled with countless ancient black holes formed in the first second of the Big Bang? These black holes, ranging from planetary mass to far larger, would be virtually impossible to see directly unless they were actively feeding. Yet their combined gravity could subtly influence the motions of stars and even entire dwarf galaxies, adding another layer of complexity to the already puzzling dynamics we observe. They would be the ultimate dark interlopers, invisible anchors woven into the fabric of galactic space. The hunt for Planet 9, then, is more than a quest for a new world. It is a test case for our ability to find the unseen by its gravitational whispers. Its confirmation or refutation will sharpen the tools we use to listen for similar whispers on a galactic scale. Every anomalous stellar motion, every unexplained wobble in a dwarf galaxy's path could be a clue. We are learning that darkness is not always empty. It can be massive, it can be structured, and it can hold secrets that rewrite the story of our supercluster's hidden architecture. Two distinct possibilities dominate the laboratory hunt, each representing a different vision of the invisible universe. The first are weakly interacting massive particles, or WIMP. As the name suggests, these are hypothetical particles predicted by certain extensions to the standard model of particle physics, thought to be heavy, perhaps dozens or hundreds of times the mass of a proton. And crucially, they interact with ordinary matter only through the weak nuclear force and gravity. This makes them incredibly difficult to detect, but not impossible. Their story is one of cosmic coincidence. In the early, hot, dense universe, WIMP would have been created in abundance. As the cosmos expanded and cooled, their mutual annihilations would have slowed, leaving behind a relic density that, through a remarkable piece of mathematical serendipity, matches the amount of dark matter we observe today. It is an elegant solution that connects the largest scales of cosmology to the smallest scales of particle physics. To find them, scientists have built exquisitely sensitive detectors deep within mountains and old mines, shielded from cosmic rays by a kilometer of solid rock. These experiments, like Xeno-NNT in Italy or LZ in the United States, use vats of ultra-pure liquid xenon. The idea is simple in principle. Wait for a WIMP from the Milky Way's dark matter halo to drift through the tank and, on a very rare occasion, bump into the nucleus of a xenon atom. That tiny collision would produce a flash of light and a puff of charge, a signature the detectors are built to capture with almost unimaginable sensitivity. They listen for a whisper in a silent room, a room buried under a mountain to keep out the noise of the universe. After decades of operation and ever larger, purer detectors, they have heard nothing definitive. The WIMP, for all its theoretical elegance, remains a ghost. The other leading candidate is almost its opposite, not heavy and rare, but incredibly light and ubiquitous. This is the Action, a particle first proposed to solve a completely different puzzle in quantum physics. Actions would be billions of times lighter than an electron, but they would be produced in staggering numbers, forming a cold, coherent wave that permeates the galaxy. Instead of the rare nuclear bump of a WIMP, actions would reveal themselves through a subtle, magical conversion. In the presence of a tremendously strong magnetic field, an action could, in theory, transform into a microwave photon. To hunt for them, experiments like the Action Dark Matter Experiment, or ADMX, use a high-precision radio receiver inside a powerful magnet, tuned to scan across millions of possible frequencies, listening for the faint, specific tone that would be the Action's song. It is like tuning an old-fashioned radio across the static of the cosmos, searching for one perfect, pure note that no natural station should be playing. The challenge is that the action's exact mass, and thus the frequency of its photon, is unknown. The search is a painstaking, inch-by-inch scan of a cosmic haystack where the needle could be hiding anywhere. Both quests for the heavy WIMP and the wispy action push engineering to its absolute limits. Their continued null results are not failures but powerful data. Each experiment that fails to find a signal rules out a vast swath of possible properties, narrowing the window where dark matter can hide. This persistent silence is itself a profound message. It tells us that dark matter is even more elusive than our best theories imagined. Perhaps it interacts with ordinary matter so weakly that our current technology is fundamentally blind to it. Or maybe our conceptual framework is entirely wrong, and the answer lies not in a new particle, but in a deeper modification of gravity, or in something more exotic still, like primordial black holes formed in the universe's first instance. The detectors in the deep quiet and the tuned magnets in the laboratory are our hands reaching into the dark, feeling for a shape we have not yet grasped. Every day they listen, and every day the universe answers with a silence that is slowly teaching us what dark matter is not. Gravity's push can be as powerful as its pull. While the Great Attractor draws us in from one direction, cosmologists have proposed a counterforce acting from the other, a cosmic emptiness so vast its absence of gravity creates a repulsive effect. This is the dipole repeller. Imagine you are in a boat on a calm lake and someone on a distant shore begins pulling the water toward them with an immense, invisible force. Your boat would naturally drift in that direction, but what if behind you someone had also drained a colossal section of the lake, creating a profound depression? Your boat would also slide backward into that empty basin. This dual effect of attraction from a mass and effective repulsion from a void is key to understanding our galaxy's motion. The dipole repeller is theorized to be a staggeringly large underdensity, a void even more immense than our local KBC bubble, lying in the opposite direction from the Great Attractor. In this model, we are not just being pulled toward a gravitational hotspot, we are also being pushed from a gravitational cold spot. The universe's expansion accelerates everything apart, but within that overall flow, the relative densities of matter create local currents. A supercluster is a hill, and its gravity pulls galaxies toward its peak. A void is a valley, and because there is less matter there to exert a gravitational tug, the surrounding denser regions pull galaxies away from it, making it seem like the void is repelling them. It is a cosmic tug of war where one team is not pulling, but simply letting go. This idea refines the picture painted by the Great Attractor alone. Our motion is not just a response to one monster, but a navigation through the full topography of the Virgo Supercluster and beyond. We are flowing down the slope of the cosmic web, from the highlands of the dipole repeller's emptiness toward the lowlands of the Great Attractor's density. Mapping these flows is like charting ocean currents by watching the drift of buoys, with each galaxy serving as a buoy in the dark sea. The existence of the dipole repeller, however, is inferred, not directly observed. It is predicted by sophisticated models that reverse engineer the observed velocities of thousands of galaxies, calculating the distribution of mass, both seen and unseen, required to produce those motions. These models consistently suggest that to fully explain our path, a vast underdensity must lie in the galactic opposite direction of the attractor. Yet, like the attractor itself, this proposed void lies hidden behind the obscuring plane of our own Milky Way, a zone of avoidance that keeps its true scale and structure a mystery. This transforms the mystery from a single point of attraction into a dynamic interplay of presence and absence. It suggests the large-scale flows shaping our supercluster are orchestrated by the entire landscape of the cosmic web, a symphony where the deep silences of voids are as consequential as the brilliant crescendos of clusters. Are we merely passengers on this gravitational current, or does understanding this push and pull reveal something fundamental about how all structure in the universe evolves? Among the fleeting screams, one voice called back, FRB 121102, discovered in 2012 and confirmed as a repeater in 2016, changed everything. This was not a single catastrophic explosion, but a source with a temper, firing off brilliant millisecond bursts again and again from the same tiny patch of sky. For the first time, astronomers could point their most powerful telescopes at the location and wait, knowing another burst might come. This patience was rewarded with a stunning revelation. The bursts were traced to a dim, dwarf galaxy over 3 billion light-years away, a small, messy galaxy actively forming stars. But the real surprise was what they found at the burst's precise home, a faint, persistent radio source. It was like finding a lighthouse that occasionally flashes with the power of a supernova, but between those blinding flashes, it constantly emits a low, steady radio hum. This persistent glow suggested an engine that was always on, a turbulent environment where the cataclysmic bursts were just the most dramatic eruptions. The leading suspect for such an engine is a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's. Imagine the most powerful magnet in the universe and then multiply that by a factor beyond comprehension. Theorists propose that this magnetar could be embedded in a dense nebula of material, perhaps debris from the star that formed it or a wind of particles flowing from its surface. The persistent radio source could be the glow from this nebula, constantly energized by the magnetar's furious spin and magnetic field. The fast radio bursts themselves might then be produced by colossal starquakes on the magnetar's crust, or by sudden, explosive reconnections of its magnetic field lines, like a cosmic circuit breaker snapping and unleashing a torrent of energy. This model fits the data beautifully for this specific repeating source, yet it cannot be the whole story. The vast majority of fast radio bursts detected are one-off events, heard once and then never again. These non-repeaters present a different challenge. If they are also from magnetars, why do they only scream once? Perhaps they are from an even more catastrophic version of the same phenomenon, a magnetar experiencing a single terminal event like collapsing into a black hole. Or perhaps their source is something entirely different, like the collision of two neutron stars, a cataclysm that destroys the engines in the process. The existence of both repeaters and one-off strongly suggests we are dealing with multiple cosmic phenomena. The universe, it seems, has more than one way to shout in the dark. This diversity makes the mystery richer and more urgent. Are we listening to the death cries of exotic stars, the birth pangs of black holes, or something even stranger? Each new detection, especially from within our local supercluster, adds another piece to a puzzle that is forcing us to expand our catalogue of the universe's most violent and fleeting events. Within that profound emptiness, the few galaxies that do exist become cosmic laboratories of the highest order. One of the most famous is a lonely spiral known as MCG plus 01020015. Astronomers have nicknamed it the loneliest galaxy in the universe, and for good reason. Its nearest galactic neighbor is over 1 million light-years away, a staggering isolation that makes our own local group feel like a crowded metropolis. To be a galaxy in the Boötes void is to grow up in profound solitude, cut off from the gravitational tides, collisions, and gas exchanges that shape galaxies in denser clusters. This extreme environment leaves a distinct signature, a fossil record of a life lived alone. Void galaxies like this one are often metal-poor. In astronomy, metals refer to any element heavier than hydrogen and helium. These heavier elements are forged in the nuclear furnaces of stars and scattered into space by supernova explosions. In a dense galactic neighborhood, this enriched material gets recycled, seeding new generations of stars with a richer chemical palette. But in the void, a galaxy has only its own stars to rely on. With fewer neighbors, there were likely fewer galactic mergers and interactions to trigger intense waves of star formation in the past. As a result, the stellar population in a void galaxy tends to be older and more pristine, with a lower abundance of those heavy elements. It is a quieter, more isolated stellar evolution. Yet, this isolation can lead to surprising bursts of creativity. Without the constant gravitational harassment from neighbors, the gas within a void galaxy can settle into a more stable, relaxed disk. In some cases, this calm environment allows for slow, steady, and sustained star formation. The galaxy is not being disrupted or stripped of its gas, so it can hold onto its fuel and use it at its own pace, potentially leading to a long, quiet life of stellar birth. In other void galaxies, however, the very lack of external triggers might mean that star formation happens in fits and starts, as the gas slowly cools and collapses under its own gravity without the kick from a passing galaxy. Studying these isolated systems is like watching a plant grow in a sealed greenhouse, removed from the wind, rain, and competition of a forest. You see how it develops according to its own internal rules, free from external influence. This makes void galaxies pristine test subjects. They show us what a galaxy is like when left to its own devices, allowing us to disentangle the effects of a galaxy's intrinsic properties from the effects imposed by its environment. Every spiral arm, every pocket of star formation in MCG plus 0102015 is a product of its own internal dynamics, a pure expression of galactic physics. By comparing these hermits to the social butterflies in galaxy clusters, astronomers can pinpoint exactly how a crowded cosmos twists and shapes its inhabitants. The galaxies of the Boötes void are not just lonely curiosities, they are control experiments in the grand study of cosmic evolution, holding clues to what our own Milky Way might have been like if it had formed in the deepest, quietest reaches of nothing. These 25 mysteries are not isolated curiosities. They form a single, sprawling frontier, the unanswered questions that define our place in the cosmos. From the ghostly pull of dark matter and the repulsive push of dark energy to the profound silence of cosmic voids and the fleeting screams of fast radio bursts, each phenomenon is a crack in the foundation of our understanding. The aligned filaments of the cosmic web, the missing lithium in ancient stars, the too-big-to-fail satellites that never shone, these are not errors in our data, but signposts pointing toward a deeper reality. They remind us that the Virgo Supercluster is not a solved map, but a living puzzle. Every anomaly, every contradiction is a gift to science, a challenge that forces us to rethink our theories, build better detectors, and peer deeper into the dark. This is how discovery happens, not by confirming what we already know, but by stumbling upon what we cannot explain. So the next time you look up at the night sky, remember you are not just seeing points of light. You are looking at the surface of an ocean of mystery, a cosmic web woven from questions we are only beginning to ask. The greatest story, the one that explains the nature of the void and the substance of the shadows, is still being written, and its next chapter is waiting in the vast, unexplored darkness between the stars.